Thank you. Nice to see many familiar faces as well. Hello. So yeah, I'm going to present on how you potentially could reduce the search space using a mineral systems approach for copper exploration. So there'll be a lot of information here. Happy to discuss things afterwards. So let's go. So first I want to acknowledge all of the people that contributed to this talk. Vincent, Joel, Clive, Andrew, Aaron, Thomas, Heather, Uli, and Carmen from the GSSA. So, you know, sedimentary basins, 80% of Australian continent is covered with sedimentary basins. But then if you look at the current mines and abundant mines and workings in Australia, this is all commodities. Looks a bit bleak when it comes to the sedimentary basins. And it's often a reason for it because you don't have the usual outcrop where you sort of poke a hole in and then find something, and hasn't been as attractive to explore in basins. So what do I mean with basin-hosted mineral systems? I'm not going to go into the mineral systems approach thing. I'm sure you heard about it. But one of the things, what we're trying to do is adapt the petroleum exploration techniques into base metal mineralizations and basins. And in petroleum systems, you have a very well-defined approach where, you know, you have your basin, so you have your basin, it fills, it buries, with that you change temperature and pressure, it creates your hydrocarbons, there's a well-defined window when they are mature, and if you understand that, you know how to explore for it. In base metal mineral systems, well, we don't really understand it that well. It's not as simple, one burial, one depth, one temperature thing. And just to show what I mean with that is, this is just a very simple sketches of various deposits across the world where, okay, we do see, so the blue is the usual mineralized horizon. It looks like it's stratiform, it follows some bedding or lithological units, but the geometries can vary quite a lot, and it doesn't really tell you at the timing of when they actually formed. So it's not like a one-time event. So it's usually, it can basically occur throughout the basin evolution. So whenever you have a fluid circulating in a basin that of course has to have the right composition, and you have to have the metals, if you get them circulating from the source to the host, then you're likely, you could be able to form a deposit. So it could be at 25 degrees, it could be at 100, 150, whenever. So what we do is we basically take the minerals, parts of the mineral system, which is source and host rock, the fluid migration and composition, but then we also add things that aren't in the current mineral systems approach that comes from the basin analysis, which is the basin evolution, Facies Analysis, the burial history, and the thermal history. And tonight I'm going to talk you through some of the components and the actual way of how we use that to reduce the search space or just explore. So looking at the components you need. So you would have the tectonic setting, continentality, paleoclimate, deposition environment, then the fertility process, fluid triggers, ore forming process, and then you could define a commodity. So that's for basins. So you can take this diagram and figure out with your type of the deposit you want to form what you need for it. And you need to do that for the source and the host. So it's not enough to just find that nice black shale that you think is going to be the host. You also need to figure out if you had the right evolution of the source rock, which could be a volcanoclastic rock that might have a higher copper concentration than your average siltstone or something. So you have to follow both, and they could potentially, they're not necessarily forming in the same deposition environment. So you've got to follow the path of both of them and then figure out if they still had the permeability, porosity, fluid flow, structures, and so on to get to the point where you kind of define that bit. And then when it gets a bit crazy, because this is all of the components, the fluid mechanisms that you can have in basins, and they all can lead to fluid circulation that might lead to a deposit. Might not be all a tier 1, but they could lead to carry metals. And this is the least well understood of which one is actually the one that plays the biggest role. And then that could happen throughout the basin evolution, including deformation, including uplift and basin inversion. The way we approach that, and it's sort of a thing that you would start with very similar things in exploring in other areas. So you use your present day data, and that's the best developed one, just to figure out your basin architecture. So you use all of the geophysical data you get and do a structural interpretation of the map, and you get a really nice picture of what you think the basin looks like at the current stage. Doesn't really tell you that much of what it would have been back in the day. If you already have a deposit in the basin, it's usually a good thing, because you have that one little piece of information that might help you figuring out where to go next. Then, so when you do this, in the ideal case, it's a study we did in the MacArthur, you take all of the different layers of geophysical data and lithological data, and you create a 3D model mapping all the different stratigraphic units plus the basement, and then you can create cross sections that what it looks like now. This is for the area for the HRC deposit. However, you don't always have, in Australia, we're lucky we have most of the data throughout Australia, but they're not always actually representing the sedimentary fill. So I'll show you an example where it's a bit more difficult. So we currently have a project with the South Australian Survey, and we're looking at the Stuart Shelf sediment-hosted copper systems the last two odd years. There's no mineralization on Mangansen, so it's outcropping. But you see this, so that's the outline of the Stuart Shelf. It sits on top of the, Olympic Dam, Prominent Hill, Carmentina. So it's like most people, they drill to find those deep IOCG deposits, but there's a whole 1,000-meter basin on top of it that also is mineralized. If there's a link, we don't know. Doesn't really matter at the moment. But we wanted to understand the basin architecture of that and figure out if there's more information on more potential for mineralization, like, for example, Mangansen or some of the other ones, and then use the geophysics. But turns out all of the geophysical data, like the gravity and the magnetics, they're mostly showing basement, something much deeper. And so we had to come up with figuring out which geophysical technique actually works. So just to show what I mean, so that's the Stuart Shelf sequence. That's Neoproterozoic rocks between the two glacial cycles. And then we've got the basement margin, but the basin consists of the Pandora Formation, which could be 1,000-meter thick sandstone. Again, nothing that has any geophysical signature. And then below you got the Gawler Range volcanics. Intruding into those, what we call basement rocks, are the Gardner dikes. So the Gardner dikes is the prominent feature in the magnetics. So what we do is we try to do a top-down and a bottom-up approach. So we're using existing AEM data and trying to process them in different ways to see if you can pull out more information that are intraformational, and then combine it with MT to map the basin-basement contact as good as we can. And then we use the semi-automated magnetic mapping of the dikes. So this is still the dike swarms, and those are just an excerpt on the points that are mapped along the dike to get the top of the dikes, which basically should tell you anything that goes to the top of the dike should be the maximum depth of the basin if they would have come to the top of the Pandora Formation. And then the gray surface here would be the depth to the Gawler Range volcanic. So you see there's a bit of a discrepancy of the basin we are interested in compared to the magnetic basement. So it's a bit tricky, and it doesn't always work to use geophysics for sedimentary basins. It's basically what I'm trying to say here. But there are other ways of getting information on the architecture, which is the Facies Analysis. And it's less expensive, and I'll show you how much you can get out of it if you haven't done it properly. So Facies Analysis, what we do is we log the core. Fortunately, because in South Australia, there are hundreds of drill holes going through the sequence because everyone wanted to go below. We logged 25 of them in a sequence stratigraphic framework. So we looked lithofacies to define the deposition environment. Most of the holes don't have gamma ray. Gamma ray is crucial. So we have a handheld spectrometer where we take the gamma ray measurements. So to producing our gamma ray curves, that helps with the correlation. Facies description of the different facies. So this is all the work that the GSSA has done in the last couple of years. And then we define our depositional environment based on the interpretations. When we take all of the data and look at along in a profile across the whole basin, so that's, 500, 600, 700 kilometers. It's all work in progress, by the way. What we see is, so in the bottom, so this is Mount Gansen area where we know we have mineralization in the Whyalla sandstone. So this is the Whyalla sandstone, the brown unit here. That's the paleo high with the mineralization. But there's also known mineralization in the base of the Tapley Hill Formation, not in this area, but across the region. So when we did the Facies analysis, we found, and we correlate the different holes. You'll see in the beginning of the deposition of the Tapley Hill, there wasn't really a hill there. So it was pretty much flat. So we know during the evolution of this basin, there's been a deepening along the flanks of this high, which would implicate that there's likely to be a structural control on that. So you would know you can identify your structures based on the sedimentology if you don't have any seismic or any other information. And then by the time you get to the Whyalla, so that's the lower interglacial units, and that's the same where we have the correlated it across when we have another flooding surface, which means it's everything is the maximum water depth. And you see again, it's by the time we have a paleo high. So it's just by locking core and correlating it, you can get information around what happened to the basin during the time of deposition. You get deepening and shallowing, and it gives you a hint of where you might have areas of interest. Because structures, as you know, they're always like the most crucial bit. Then we go look further in what else we can collect on the drill course that gives us information, and so we going deeper into the higher details. For that, we use, for correlation, we also use the carbon isotopes, which is very sort of a confirmation of our interpretations by numbers. But we also look at high logger data. This is a composite of the mineralogy of the different units, and as you see, doesn't always work in everywhere, that the stratigraphy correlates with our facies, and it correlates with packages of a very unique mineralogy. We can use that information because we know, if this package here, it might look the same in core if you're not that familiar with sedimentology. It has a very different composition from this one. It has also implication on if that's a viable host, because you have to understand the mineralogy in order to see if there is a potential for if this retaining permeability, porosity, or reactivity. I'll show you in a minute what I mean with that. And then we can play around a bit with see what the variation is across the mineralogy within the facies. So it's not likely to be homogeneous across the basin. So if you want to go, one of the ideas in the Tapley Hill, for example, is you want to have those high carbonate contents on the base because it creates secondary porosity, but it might not be present across the whole basin. So you want to know what the distribution of that is spatially. And with that, we also collected handheld XRF data just to see what the background is, and you'll see that there's a bit of, that's for all of the drill holes, is a bit of copper sniffing around. I'll show you something else in that regard in a minute as well. And then, because there are a lot of holes that have high logger data and you can't log every single hole manually, we use automated multivariate boundary detection in this case. So it looks at the high logger, each mineral group, and then it creates an automated boundary where there is a massive break. And if you then sort of just, those are the lines that been detected, and then you can see it picks up the stratigraphy actually quite nicely. So it's just another tool that helps to automate things a bit. So if you have 100 drill holes with high logger data, you can just first pass, you put it in there, run through. So what do we do with once we've done that? We're going into the basin evolution because we know what it looks like now. We know we've identified the facies, but how did we get there? How did we get that one drill hole? Is it 1,000 meters? The other one is 400. One is outcropping with the same stratigraphy. So for that, we are diving into the basin evolution. The first thing we do is, so this is, by the way, you can download it from the GSSA webpage, the current Adelaide Rift area. So this is all the copper occurrences throughout. And those are the current position of some of the stratigraphic surfaces, Tapley Hill and Whyalla. And what we do is for each drill hole, we establish a burial history curve. It's a very common thing to do in petroleum, but it basically tells us the evolution through time for the drill hole, taking into account the permeability porosity changes. So it calculates how deep it's been buried throughout time, what's happened to it, and then it allows us to evaluate if there have been, so you see this unit here, it's getting buried, and then there's an uplift. So you can already see that there's mechanisms going on based on this that could have played a role once we thinking about when we create fluid trigger events, fluid flow events. So that's on the drill hole, but then we don't really know what the mineralogical alterations or the diagenesis is in those holes. Why is that important? Because, you know, diagenesis first is a mechanical compaction, and then you go into chemical compaction. During that, you have a lot of porosity loss, depending on it's a bit different, the curves, depending on if it's a sandstone or siltstone or shale. But if you have no porosity left or permeability left, you're not going to get a deposit there at even if you have higher temperatures. So that's sort of closing, you know, that sort of takes away the possibility, even if you have later fluid flow, to get anything in there. And you got to consider that again for your source and your host. Your source might not be on top of the below the host. It might be a few hundred meters below or half a kilometer below, which then could have had a very slightly different path in terms of retaining porosity. And again, this is sort of a similar plot I just showed, but it's plotted by temperature. You have it's a bit like, you know, in the metamorphic world, you got your metamorphic grade mineralogy that is very well-defined temperature pressure windows. You have a very similar thing in sedimentary systems, just lower temperature. So we know, you know, you got dolomites forming, for example, at low temperature. You got Ferrone dolomite is usually the later thing. The quartz cement starts at a certain temperature. So you can use those indicators, when you identify those minerals, cements, you could then postulate what the actual temperature was during that time in the burial, which helps you sort of which equates to a depth. So you kind of, you know, at 100 degrees with a normal geothermal gradient that's been buried for 3 kilometers, and then you can estimate the porosity at that time, if there's any left. And then again, if it gets uplifted, you might create second bonds. So I'll show you an example, again, from the Stuart Shelf, what that means with regards to a bit of copper mineralization. So we're looking at another drill hole in the Stuart Shelf. So that has, so this little plot, you see it's copper. So you see there's a bit of a sniff in there. It's just a drill hole. It's nothing that people targeted for a massive mineralization or anything. It's just pretty much background. But again, you got a bit of a sniff in the top of the Whyalla, and then you got a sniff on the base of the Tapley Hill. I only show you an example from this bit. So we look at the core, you see it's a pretty ordinary sandstone, but then something is going on here. You get a bit of fracturing, something dark. It doesn't look like a normal sedimentary feature. It doesn't look like a fault either. So it could be a fracture, it could be something else. It looks like some fluid's gone through that, right? In thin section, so that's again, all the white stuff is usually quartz grains, medium grain sandstone, which is from this area. All the black stuff, those are all sulfides, and you see they're not evenly distributed. So you got like almost like a front here that could indicate sort of the fluid flow mineral reactions. So if you go into detail on that, show you some SEM images. So first of all, we established that's all work in progress, the diagenetic power sequence for the entire unit. It's not just for that sandstone, it's for the entire sequence. And with that, we got, and it's very normal kind of things, you got K-feldspar dissolution, that's sort of early diagenetic. Then with the burial, you got the quartz cement coming in, Ferrone dolomite. But what we see is calcite replaced, this is calcite, then it's replaced by the copper sulfides. And then the copper sulfides are replaced by these arsenites. You don't get calcite. And then this is happening after you have the quartz cement. So something has happened to get the fluid, the mineralization in there. That's all happened after the burial. And it had to be uplifted again to get some meteoric, so calcite forms usually from meteoric water. The meteoric water coming through there with some copper in there to get mineralization. So that throws all of this early burial mineralization models out of the way, and it's probably more likely related to some late fluid during uplift. That's my first guess. We haven't figured the whole story out. And again, this hole is, I think it's sort of close to the edge of the Penati High, so the Mangansen area. So you could have a structurally control there, but it's hard to tell if you only have one drill hole. In order to test that, so now this is how far we've gotten with the Stuart Shelf project. So now I've got to revert to some more generic plots, unfortunately. We can test that if we reconstruct our basins. So I showed you the Facies diagrams where you can see sort of there's some structural thing going on, not quite sure. So what we can do is, if we have a good cross-section of what it looks now, so I'll make it a bit more complicated here because it's more reality in most areas. So imagine you got sort of an idea of a cross-section representing your current geometry. Is quite folded, it's been inverted, it's almost like an orogenic belt. You want to know where you might have the potential to have mineralization. You want to know which faults might have been fluid carriers at any given time throughout the basin evolution. So we would reconstruct that to what it was in the beginning to be able to predict which faults might have carried fluids. This is only 2D, so we want to bring that into a 3D space, and we want to add the sedimentary fill, because at the moment you just got a bunch of structures. For that, we do stratigraphic forward modeling. Some of you might have heard of it, but basically it fills the gaps between where you have drill hole data. So you got the drill hole data as your control points. You know what the facies is. You can simulate what the basin fill evolution might have looked like based on the drill holes that you intersect. And with that, you're also measuring rock properties. In this case, is the shale content during that evolution. So you would you reconstruct your architecture how it looked like when you formed it. Then you create a stratigraphic forward model to get the filling right, and then you can take it back into the geometry that you see at the current stage. So now comes the fun part, which is also the most difficult one, and that's the simulation and scenario testing. So you want to test what the potential was at any given time to carry fluids, assuming we have a host and a source rock. You're carrying the fluids through the system to a place where you might expect mineralization to occur. It potentially could, reduce your faults that you have in your area to half, because some of them might have never been able to carry any fluids because they were not open enough. Anyway, so an example we did in the MAGWA Basin. So you take your stratigraphic model, you take your structural model, and then you predict the fluid flow. So in this case, all of the arrows is where fluids go along the faults, but then also because we have the stratigraphy or the lithology, we can predict if it actually goes into the units, into the sediments, because we can predict the permeability, porosity, because we kind of already established the basin evolution. And then we can sort of say in this area, see, it's not evenly distributed. So you kind of, this would be your area, probably unlikely for exploration, but up here might be a bit more of a target. So by presenting that you see that there are a lot of steps you can take, or you should take, or should consider when you explore for copper, because going back to this early image, you don't know when that timing was of that mineralization. It's a good guess that some of them might be early, late. You can see that is likely to be a remobilization effect as well. The one I showed you was near Mount Gunson, so that could give one explanation, but so there's a lot of variables that should be considered and make it complicated. So back to my original title. So copper exploration and sedimentary basin reducing the search basin mineral systems approach. I didn't give you the full answer because there isn't an answer. There's still a lot of data lacking that really understand the relationship between all of these parameters. And you don't know the timing was right. So even if you've identified the faults and everything, you still have to have the fluid going through the source and then transferring it into some host. So, what is the chances of having all of these components happening at the right time? So yeah, so that's my presentation. Thank you very much.